Hey everybody, and welcome back to Linear Algebra Online. So today I just want to spend some time to review some of the big ideas from this last chapter that we just covered. So let's just jump into it. So we've got a question here that says, determine whether these vectors span R3. So there's basically two ways, and they're both kind of similar, that I kind of think to do this. So one way you can think about it is if you've got three 3D vectors, right? So let me try to draw this a little bit. So let's say you have, your three coordinate axes there. If you had three vectors, like 1, 2, and I don't know, 3, or something that are linearly like independent from each other, so they're not like in line with each other, then basically they would span R3, right? So one way you can set this problem up is you could just take, you could create a matrix of like these, you could really do it as row or column, but you could basically, I'm going to stick them in as column vectors. So V1 right there, V2 right here, V3 right here. And then I'm going to just augment this thing with the 0 vector and basically just do like RREF on my calculator. And if you do that, you get 1, 0, 2, 0, 0, 1, negative 1, 0, and then a row of zeros. And so what this means is, basically like if I had this picture, right, these three vectors would, independently from each other, they span a line. And if they were linearly independent like this, there would just be like a common point of intersection between those lines. And this system of equations does not agree with that idea of a common point of intersection, right? This row of zeros means that really like there's, the dimension of intersection is actually not just a point, right? Because points in a reduced matrix would be something like 1, 0, 0, 2, 0, 1, 0, 3, 0, 0, 1, 4. And like the point is, 2 in the x, 3 in the y, 4 in the z. But that's not what we have. We have a row of zeros. And so there's like a line of intersection between the three vectors, which means that, there's some dependence going on here. So that's one way to think about it. So no, to answer the question, I guess. Another way you can just do it, so you can take this, you actually do, I don't know if it'll work on like TI-84s and things, like I can do it on an Inspire, but you could also like do this with like, most people in the technical world would really just pull up like a Python terminal or something. So like any kind of high-powered technical thing could do this, but you could basically augment with like an arbitrary ABC vector, and you would just sort of see that you're just going to kind of reduce this one, and if you do RREF on that, and you get some sort of equation, I guess we'll call it, or expression for A, B's, and C, and A, B's, and C's that is actually well defined for all A, B, and C, then it would span R3. Because then you could plug in anything here. But like you might get somewhere in there like A plus B over C, and that thing is not defined everywhere. Like specifically if C equals 0, right? That would be an issue. So if you get some sort of expression that is well defined for all different possible real values of A, B, and C, then, this would actually span R3. So I think this is personally the easiest way, basically just thinking about it with linear independence. So, checking for span and things is like it's something that's kind of just so fundamental to linear algebra, and the idea of just this row of zeros basically means, no, it's not going to happen. It reduces down to like a line of intersection, not a point of intersection like this. All right, so this is just kind of built off of the same kind of idea here, just to kind of make it a little bit more clear, I guess. So these are the same vectors from the previous problem. So if these guys don't span R3, then the three vectors, like we said, are linearly dependent, right? And if I want to prove it, right, then it would basically suffice, right, to show that, because like if three vectors are linearly independent, and you have like C1 V1 plus C2 V2 plus C3 V3 equaling the zero vector, if like these guys, if V1, 2, and 3 are linearly independent, then by definition that thing would imply that C1 equals C2 equals C3 equals 0. It's the only way for it to be equal to the zero vector is if those coefficients are 0. That's just like the definition. So we basically need to show that, like, really you could do it for any one, but I'm going to just show like V1 can equal something in terms of V2, like plus something in terms of V3, because that would mean, V1 then depends on V3. And to do that, you just go back to the the reduced row echelon form of the matrix. So I'm just going to pull it from the last slide and just copy it down here. All right, so that was our reduced matrix. And then, if we look at what this is saying, it's basically saying, so I'm going to think of this as like, C1, C2, C3 in terms of like, how much of this first vector I have, how much of this second vector, how much of this third. So it's basically saying that C1 needs to equal -2 of whatever C3 is. And then it's saying the second line there says C2 needs to equal C3. So really, as long as you follow this kind of rule or instruction and put whatever you want in here, you actually should be able to build V1 this way. So if you take now you can just sort of let C3, let's say, equal 1. So then C2 should be 1 and C1 should be -2, right? And so how can we get V1 from V2 and V3? Well then, we have that C -2 V1 plus 1 V2, so V2, plus 1 V3 should equal the zero vector. So then V1 would equal minus V2 minus V3 over -2, which is V2 plus V3 over 2. And we can check it. We could just do 1, -1, 4. And hopefully that is equal to a half of this vector 2, -2, 1, 3, plus a half of 4, -3, 5. And I'll just kind of go through one of them. But if you take -2 divided by 2, it's -1, and 4 divided by 2 is 2, and -1 plus 2 is 1, and you could just keep doing that. -1 does equal 1/2 minus 3/2, that kind of thing. So you could check it, but really this thing has told us how to build say V1 out of V2 and V3. And I kind of didn't give myself a ton of room, but geometrically, if those vectors don't span R2 and there's some dependence going on, right? They don't span R3, then they span R2, specifically actually a plane, not necessarily the XY axis, but some sort of, you have 3D space or something, and there's some plane that I don't know, cuts through the origin or something. It could be at an angle or whatever. but it's some sort of plane in R2, or embedded in R3, I guess. But it's like analogous to R2, basically. So that's kind of like a lot of really important things, honestly, from that chapter 2, all into like, 2 problems already. I've got a few more things I want to talk about, but this is kind of like one of the most important things, I would say. There's actually a theorem that we never proved from this unit, and this is it right here, but it's so like short, and the proof isn't really super informative. It's one that I think is honestly a good time to talk about how important it is to just make sure that things like this you see in the book make sense. So a lot of times before you can even prove something like this, you want to wrap your head around what it's saying. And, if it's a theorem, you know it's true, and like you can read the proof in the book and stuff, but you should be able to like envision why these things are true. So what this is saying is that if you have m vectors in Rn, but m is bigger than n, then that set of vectors is linearly dependent. And like the way I think of this is, let's take like n to be 2, right? And then my vector set to be something like 3. -4, 2, and 6, and pi, because why not? So this is basically saying n is 3. This is saying n is 2. I believe 3 is bigger than 2. And it's definitely true that there's got to be some sort of dependence amongst these. We could go through like the exact same kind of argument we did over on this problem, and figure out like how we could build 1, 2 out of this. But the idea is just like, if you're in, say 2-dimensional space, you're never going to be able to have 3 linearly independent vectors. If you're in R2, you can draw one arrow that way, and you can draw a second arrow in a different direction. But now, if I tried to draw any other arrows, this green one or something could be built out of the other 2 I have, right? Basically, this stuff already spanned R2, so adding another vector is just not useful. It's not going to add anything else to this, basically. So, you can read the proof. I don't want to prove it because it doesn't, I think, help as much as just thinking about what it says. But whenever you see these theorems in the book, take the time to do this kind of stuff. Think about what it's saying before you think about like trying to prove it in general. It's going to help you a lot if you can like wrap your head around what something is saying. All right. So I've got these 2 vectors here, 1, 2, 3, and 2, 4, 6. And I want you to think about describing the span both algebraically and geometrically. So if you look at it, right, 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6. So these 2 vectors are really just like scalars of each other, right? They're parallel vectors. And so geometrically speaking, they span a line in R3, right? And like algebraically, how we would write the span is basically a vector form of a line. We would do just like x, y, z equals some scalar on like 1, 2, 3. And that's like, these spans, when we talk about spanning sets, we always think about them being lines or planes or whatever that go through the origin. So, I'm not writing it, but basically there's like a +0 vector here. That's sort of like my point vector, like we do in Calc 3 and stuff like that. Typically I write this first and then I write this part second. But you don't really want to write that. It's not useful because they all like go through the origin. But this is algebraic and this is geometric. Then if you think about changing like the 6 to like say a 5, okay? That's going to change a lot now, right? So now, geometrically, this thing is going to span a plane in R3. So again, it's going to go through the origin. And in terms of a, what's the word I'm looking for? A algebraic representation of that plane, we would just have like x, y, z. And we would have like, let's use s maybe as a scalar. Then you could just pick 1, 2, 3 as a direction vector. And then like t times 2, 4, 5 as another direction vector. And again, you don't need the 0 vector. You can put it here, it doesn't matter. But basically, it's just a plane through the origin now, right? And that's just because this new vector 2, 4, 5 is like out of line from that guy a little bit now. They are going to be independent from each other. And so you'll get a plane's worth of stuff in the span. And say you had the 1, 2, 3, the 2, 4, 5 vector, and you wanted to span R3 from using those two and another one. The tool we often use in math to do that is the cross product, right? Like a lot of my friends are PhD students and engineers, and one of the things that they do oftentimes, they need to figure out a way to describe 3D space using maybe building it up out of different vectors. And if they find two like this, they can guarantee themselves another one if, say this is my 1, 2, 3, and this is my 2, 4, 6, they could do their cross product, and it's kind of hard, but like this green one sort of comes out of the page, but it's like perpendicular here, and it's perpendicular here. It wasn't a very pretty picture. I'm going to do that better because my OCD. Perpendicular there. I like that better. And then perpendicular there. The cross product is very useful if you ever need to create another vector that's going to span R3 or something like that, if you have two that are already independent. All right, this is just a good concept question. So what is the maximum rank of a 5x3 matrix, and what's the minimum rank of a 5x3 matrix? So rank, again, very important definition. You definitely want to just know this one off the top of your head. So this is the number of non-zero rows in row echelon form. Okay, and basically, if you've got a 5x3, okay, so we go 1, 2, 3, 4, 5. Again, my OCD. Let's do this. 1, 2, 3. Let's say. So say you have a matrix like that, right? This thing. Basically, we have a situation that is like 5 vectors in R3, right? And 5 vectors in R3, right? You can draw 3 of them. 1, 2, 3, let's say. You can think of that in R3 and have 3 linearly independent vectors. But if you have 5 vectors in R3, right, you're going to definitely get some 0 rows. And you could have 3 that are linearly independent, but then any fourth one I draw would basically somehow cancel out in the matrix reduction, and you'll get a 0 row. And a fifth one would also cancel out. So you could have basically 3 left over, but you'll never have all 5. So the max rank here would be 3, and it's really just because you want to think 5 vectors in R3. That's basically what that problem would be if it was 5x3 matrix, right? And if that doesn't make sense, maybe think about a like a more simple example, like if you have a matrix 1, 2, 3, 4, we'll say 5, 6, 7, 8, 9, 10, 11, 12. So if you take that matrix, right, you can think of this as like a system of 3 equations, like 3 planes. And I think that might make it a little more sense to you as to why this is 5 vectors in R3, basically. But anyways, the max rank, definitely 3. The min rank, there's nothing to stop you from saying that the min rank would be 0. So that's kind of like a given, I guess, with any matrix. So the min rank for any matrix really would be 0. You could always just have like a bunch of 0 rows. There's nothing to stop you from that. Like the whole thing could just like cancel out to 0, basically. So max would be 3, min would be 0. All right, so this last thing I want to do is just prove that every subset of a linearly independent set is linearly independent. And to do that, I'm going to just kind of turn this first into a little bit of symbolic form. But actually, maybe this is a good time, too, to say, let's make sure we think about these things, like I was saying a little while ago, before we just jump into it. So it makes sense, I hope, that every subset of a linearly independent set is linearly independent. Like, it'd be very weird if you had, 1, 2 vectors in 2D that were linearly independent, and then you took a subset, like 1 in this case, and that all of a sudden became dependent. Like, it doesn't make sense. If you have 3 vectors in 3D that are linearly independent, and you take away 1 or something, a subset of those should still be linearly independent. So that's all this is saying. It's more of a practice in like notation and how we kind of prove something. So I'm going to just kind of define a few things. So I'm going to say let S be a subset of T. So S is like the subset I'm basically going to show is linearly independent. And I'm going to say maybe like comma where T equals like this set V1 ... up to like Vn of linearly independent vectors. So to start off, I'm going to take, I'll call it like V1. Actually, I'm going to change this a little bit. I'm going to take C1 V1 plus C2 V2 plus ... plus CK VK. And I'm going to set it equal to the 0 vector for V1 comma VK in like the set of these in S such that K is less than or equal to N. So basically I'm just saying take a linear combination of the vectors in S and set it equals 0 vector, and I'm going to, like we show, that the only way for this to happen is if these different C's are equal to 0, right? That would prove that the subset is also linearly independent, okay? And it's pretty short. So we could say since V1 ... VK is in S and S is contained in T, we have that V1 ... VK is part of T. And then we could just say note T is linearly independent. So V1 linearly independent set, I should maybe say. So V1, so C1 V1 plus dot 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 plus K VK equals 0 implies, 0 vector, implies that C1 all the way through to the end of these is 0. And that is basically it. This implies that S is also a linearly independent set. That's it. So it's mostly just a good demo of kind of how we can put some notational rigor to something like this. So it's one of those sometimes where it's so simple that it's hard sometimes to prove these things, but this would be a perfectly good way to go about that.